Start recording.
5 p.m. in the morning.
5 p.m. tomorrow, I will have extra review session, and you can come. If you don't come with your questions, you can email me questions, and I will answer them, and then you'll see the recording, and it's be fine.
There's actually a lot of emails.
But the exam starts with polar coordinates questions, and then everything else is integrals. So polar coordinate question, I left it to be very simple. Your job is just to remember the formulas, which are, that was the last one left from the multiple integral chapter, if you remember. Not polar coordinates, spherical coordinates, yeah.
Dang it.
Spherical coordinates. There used to be more problems there about spherical. I just kept one. Spherical coordinates. So if you don't get it, some people complain they still don't get it. So it will be one multiple choice, and it's not too bad. Your job is to remember the formulas, and that is kind of challenging, I have to say. But at least I made it simple, so even if you forgot formulas, to be honest, you can still do it. Yeah. X squared plus y squared plus z squared is rho squared. We remember that. Where in three-dimensional situation we have in 2D, there's only one variable now. This is theta. Theta is running from 0 to 2 pi in 2D. Now everything else is in 3D. The point has a radius in 3D, and that's why it's called rho, not r anymore. But it's still just positive or 0. And this is how far I am from the center, but in 3D, like a fly is flying in the air. And then there's a phi, the angle with z phi. Phi was restricted from, do you remember? Good job, from 0 to pi. So your job will be to recognize this, and there's a formulas which are the challenging ones. So you need to know these, the idea behind them, to build. If I tell you it's in the first quadrant, you immediately need to figure out, oh, so phi is from 0 to pi, so in 2D is the full rotation or not. First quadrant explains you stuff. I want to write down the formula first and then do the example. X is, maybe this way it's easier to remember, r cosine, so rho cosine. Y is r sine, so rho sine, but the additional part is, the first one has sine phi and the other one has sine phi as well. So that's the difference between polar and spherical. Some idea is the same, some is not. And then z left, blue color. Z has rho, and now that one is missing, which is cosine phi. So maybe this is the way you can remember it better. Or from the triangle, yes.
Oh, sorry. Can you go forward? Oh, for the phi, is it always 0 to pi?
It depends. If it's more restriction, it might be not. So it's going to be from 0 to pi or 2. But the largest one, we always say largest one. The largest one is from 0 to pi.
Professor?
Yes. What?
Can you show an example where there's more restriction?
Yeah. That's what I'm doing right now. Yes?
On the graph 3, are the symbols going to look like that, or are they going to look like the basic book notation?
This is such a weird question. Why you guys don't like my phi's? So offensive. They are not the same. So why you care so much? You like this one more?
I like that notation.
So I'm not sure if I
like that one.
Damn.
But you have, okay, let's just do exceptional one. So there are not so many choices. It's either a circle or a wiggly part or a row. What is your problem?
He doesn't really.
Okay, I guess I can make, since you're requesting, which one do you want me to put? This one?
This one.
Yeah, that one. No.
No, not that one.
Not that one.
He's keeping your.
This one?
No, I learned the other way.
Okay, in class you can ask me if you get confused. I'll be like, yes, this is fine.
I'm not in class.
Ask your.
It sounds like a you problem.
Anyway, you guys should know both.
Let's just keep going.
Hey, man.
Keep moving. Let's keep moving. So you should know both, okay? Just learn that both are the same thing.
Which symbols represent that one?
Phi. So, that's all. Okay, that was not a lot of examples here. So the restrictions are, for example, This one is not too bad, I think. Oh, it's from your homework, nice. The vertex, the cone, yes. For example, the cone, example. The cone, and sometimes we might say, what kind of coordinates is this? Oh, actually, there are very nice examples over here. Let me scroll down for you. More questions, ask me why I'm doing this. I remember now, that was some questions from the exam review are very good for the exam, so I definitely recommend you, and I'm talking about these, I definitely recommend you to go over these reviews, these ones. These smoking exams are good. There's lots of questions really looking like this. So here's the first example over here. This is kind of exactly what we need. Consider the tetrahon, blah, 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 or spherical coordinates, change to spherical coordinates. Let's see, equation in spherical coordinates. Changing it is important, and sketching the graph is important. Let's see. So, number 2. Two spherical coordinates. So we give you the integral minus 2 and 2, integral for minus square root 4 minus x squared and 4 minus x squared, and integral from 0 to 4 minus x squared minus y squared, e to the x squared plus y squared plus z squared, d, z, dy, dx. How do you work with this? You first take your pencil and write down which variable means what. Z is from 3D object 0 and to this 3D object square root stuff. Then we're going to 2D right now. Y is from here to here, and then x is from minus 2 to 2. Those are numbers. You sketch the graph, and this ends up to be exactly first quadrant. With D at the end or T at the end? Quadrant. Who knows? T, right? Mm-hmm.
Yeah.
Thank you. So, how do I know? Because you will have, so either we tell you it's a first quadrant or we don't tell you. I kind of prefer to tell you because it's faster. If I tell you it's first quadrant, it's actually giving away this information. You sketch all the graphs and you see that, oh, this one is circles actually. I see. First quadrant was the other one. Okay, fine. This one is a circle. So let's draw it in 2D really fast. A circle. How do I know? Because y equals square root of 4 minus x squared is y squared equals 4 minus x squared. That's a circle. Y squared plus x squared equals 4. Radius is 4. So now we do know what 2, thank you. We do know what theta is doing. Theta is doing full revolution because I just drew it. Because not necessary. Okay, but we at least know that. Okay, not necessary. When you created the square root, when you jumped away from the square root to normal one, you're kind of losing the restrictions. That y was from minus square root to plus square root. So y is your height. Y used to be from minus square root to plus square root. There is a minus here. Thus, it's going from here to here. So
X is from negative 2 to 2 though.
x is from negative 2 to 2. That is also correct. 2 to 2. So we need to do, it says theta is from pi over to 2 pi. So it is from pi over to 2 pi. So how much?
If that were the case, wouldn't y be from 0 to positive square root of 4 minus x squared?
Or it should be negative 2 to 2.
Oh.
Negative 2 to 0.
Yeah.
No. Okay, I got it. I just mixed up 2 examples. I see. Yeah, I see. The
First quadrant have to do with this, like.
no, first quadrant, sorry, scratch that.
Oh.
I mixed up the previous example here.
Okay.
So theta is doing the full rotation as a circle from 0 to 2 pi. At least we have this. Now we need to figure out what rho and phi are doing. Rho are in 3D. That will be simple one. We already know it's going from this 3-dimensional object. This 3-dimensional object is also has radius 2. So rho in 3D is from 0 to 2. And now the hardest one is phi, and it's always the hard one. I try to give you easy examples when it's not very tricky. In this case, since z is only from 0 to up, going up, then it's not going to go the whole thing from 0 to pi, and only going to go half of it. So because, I would say, because BC, z is from 0 to a square root positive 1, then I can say that phi is doing only half work from 0 to pi over 2. Now all is ready except one thing, which is the easy part. So this was the hard part. Theta is a full rotation. Rho is going in 3D from center to the fly in the air from 0 to 2. Phi is the angle with z, but z is only positive, so it goes halfway through. So the integral will be d rho d phi d theta. You choose, but we're gonna give you multiple choice, so you kind of have to choose from the list. Let's finish just a second. Theta is from 0 to 2 pi. Phi we chose from 0 to pi over 2 halfway through, and rho is from 0 to 2. Now the last part is to figure out what's inside. Formula says there is always something inside part of the formula. Who remembers what it is?
Rho squared sine phi.
Rho squared sine phi is part of the formula. It's your tail. That is, to be honest, what is dz dy dx is converted to. Dz dy dx were converted to this tail. It's like a huge tail at the end. You have to memorize it. Whatever before that comes from the function. The function is this, and it is pretty simple. X squared plus y squared plus z squared is e to the rho squared. So don't forget to multiply by that. Maybe there's a rho pops out, and so you have to multiply by rho and so on. E to the rho squared, and you are done. This is the rotational one. First quadrant gives you restriction that something happens with phi, for example, and so on. So one question on the exam like this. That's it. That's all. Yes.
What would an example be? Like, phi would be from 0 to pi.
From 0 to pi, when it's going to be a whole, I would say double cone example is a good one. I think.
Do we have to first look at z in order to figure out what?
Yeah. I would look at z. So phi by definition is the angle with z. So z dictates how far phi goes. That's exactly how it works.
In this equation, z is to a square root, so it can only go to a certain height.
So yes, I would say this was the example of like a sphere, but only upper half of it. So phi can only go from 0 to pi over 2 up, like so. If you have a full sphere, it will be from 0 to pi, and then a cone from 0 to pi over 6, maybe it like stacks at pi over 6. Yeah.
If it wasn't from 0 to the square root, then it would be from 0 to pi.
But no. Wouldn't it be negative pi over 2 to pi over 2?
Yeah, that's a good question. Usually we do it like so. Remember, we have it in these notes. Remember how spherical works. Spherical. When you work with the cone, this is the best explanation, is to see the cone. The cone was restricted to pi over 4 angle only. Then phi is from 0 to pi over 4. Phi is how far it unfolds from z. And then when it goes down, it doesn't go from minus pi over 2 to pi over 2. When it goes to the bottom one, we're just adding pi, so it's going to be 5 pi over 4 or so on. Whatever you do to make it jump to the fourth quadrant, you just do the shift. We had this example in the notes over here. See, if you want to build this one, that will be 5 pi over 6, like so. So that's why to keep, of course you can say from minus pi over 2 to pi over 2, but we just made it to be restricted from 0 to pi completely. So to avoid getting it negative, you cannot use minus pi over 2 anymore. To keep it positive but represent this angle, you just do a shift. Make sense? 5 pi over 6. Yes.
Are we gonna have like one of those weird like pi over 3 angles on the column?
Yeah, I excluded the complicated stuff. It will be very fast multiple choice question. You will only get maybe confused between what phi is, pi over 2 or pi, but it's gonna be at least fast. So, and I'll try to make it easy.
Can you go back to the example that you showed?
Mm-hmm. Where are we? Here. 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 Yes. Okay, good.
So I'm so confused on why that's 0 to 2 and 0 to pi over 2.
Yeah, 0, 2 is rho. Rho is radius. Radius. How far I am away from the middle of the sphere, for example. So, how far I am away, this is my rho. To find away how big the sphere is, I looked over here. This one. I wrote down z equals this part. Z equals the square root of 4 minus x squared minus y squared. Square both sides. Z squared plus x squared plus y squared equals to 4. Oh, so the radius, maximum radius is 2. Rho can be 2 as a maximum and 0 is a minimum.
Okay.
Make sense? Yeah, that's a good question. And then 2 pi is what happening with rotation in 2D. When I looked the shadow of the sphere in 2D, I saw a circle, and the circle was completed. If the circle is completed, then theta was rotated from 0 to 2 pi. If it's only first quadrant, from 0 to 2 pi over 2, and or pi, and so on. Yeah. So if we tell you first quadrant, you also should pay attention to that.
But then how is the other one pi over 2?
Pi over 2 is phi. Phi is restricted in general. Phi is from 0 to pi. But this time, z was only positive. Phi, by the definition, is the angle with z. Since z was only going up, we had to restrict your phi to halfway through. So phi was only going from 0 to pi over 2. Nothing more than that.
Well, I think the arrow should be pointing the other way because it's the
Yeah.
from the zx.
Yeah, exactly. It's like so, I would say. Yeah, good point. From 0 to pi over 2. So it doesn't go, if it goes down, then it will be a complete, you should think about it as a north and south pole. That's the idea. So we only have one pole. That's why it's halfway through from 0 to pi over 2. If we hold the full rotation of up and down, north and south, then it will be from 0 to pi. So this is full rotation north and south pole, but we only go up. So we only go to north. Then it is from 0 to pi over 2, north only. Like so. Maybe that's a good way to explain it. Yeah. Makes sense? It is a little bit weird.
Yeah.
Yeah, can explain more on Tuesday if you want.
Okay.
Yes.
So, do you have enough time to like show an example where it's gonna be from 0 to pi?
Let's move on. I'll show them tomorrow then.
Okay.
Yeah, and the practice has lots of these, I think. The practice exam. Yes.
So, I'm a little confused. I did this problem last night, and I think the key says negative pi.
Let's see. My key says...
Or is it negative pi? I don't remember it being 0.
Oh, well, this one. I took it from number 2 in this review. Here. So, I kind of agree with this answer though. And also, you should definitely exclude, you see the full rotation to D, so it should be from 0 to 2 pi for theta. So, definitely exclude this one right away. Then, make sure inside part matches, that's good one. And then, you need to see the radius. Radius is from 0 to 2, okay, that's good. And then, you just compare these two. One is from 0 to pi over 2. The other one is from 0 to pi over 2. But this one doesn't have rho squared. Oh yeah, the inside part will tell you. So kind of you can do exclusion method if you want from these problems. I would say I agree that it's going from 0 to pi over 2 because this is positive. Z is from 0 to up. So to go to the north pole, it's halfway through only from 0 to pi over 2. Yeah. Not too bad. I can see this is the most confusing part. I always say students stuck with phi. I would imagine it as a north pole. If it goes halfway through, then it goes halfway through. So for, yeah. Okay, I think that's good enough. Let's move on to line integrals because that takes most part of the exam. Line integrals are everywhere. So let's do that.
Are there going to be a couple questions about conical? Or What was the other one?
Cylindrical?
Cylindrical.
No, no cylindrical, no, nothing else, just spherical, one problem, move on. So if you're not good at that one, it's just 7 points. Not too bad.
Just 7 points.
Right?
Just 7 points.
But you still can get A if you did not mess up.
7%. No big deal.
Yeah, only 7%.
With no partial credit.
No, it's more than 7%.
Yeah, that's true. Okay, don't make it sound
If I
scary.
show a lot of work in multiple choice, can I get some points?
Don't make it sound so scary, okay?
But it is scary.
I'm more scared of multiple choice than any other part of the test.
Line integrals.
Free response I can usually get through.
So, we did have lots of stuff in vector fields, but actually we're not gonna ask you to choose vector fields. It was an exam first, I deleted it with pictures and stuff. No choosing, no like weird stuff. So most of the stuff is to actually build something. The thing is you should remember is, let's see, conservative stuff, line integrals, and all of that. So that is pretty challenging, so let's review stuff. Do you remember the idea of the conservative vector fields and how to build the gradient and how to build the gradient, for example, gradient field. That is the easiest question on the test, to be honest. And I was thinking to leave it there or not, and I just like, yeah, let's keep it there, it's fine. So if you have f is given as x squared y minus y cubed, then they ask you to find the gradient field. Well, guess what? It's just lots of derivatives, you know? And the thing is, sometimes we're gonna ask you to find the opposite, and if it's multiple choice, you can just check by differentiating. So to be honest, you can just guess. The first one you differentiate with respect to x, it will be 2xy minus 0. The second one differentiates with respect to y, x squared minus 3y squared. Done. So it's very nice. Those are very nice questions. Kind of, yeah, you're supposed to be good with that.
Is that the free response?
Free response? No, probably not. Now, then we learned lots of stuff about line integrals, and that's the confusing part. It's just too many of them, too many different things happening with line integrals, and they explain different things. So let's try to figure out what is the difference between all of these. So triple integrals, spherical, skipped, that's good. Evaluate this and that with a given circle, this and that. So let's do that, right? If you see line integrals, if you see the integral with ds at the end, right, that should give you a hint that will be a formula with a huge square root at the end. So I would try to recommend doing this one. If I put ds there, that's a hint for you that is the formula that requires a huge square root at the end. What kind of square root? You need to find derivatives. dx with respect to t, dy with respect to t, dz with respect to t. If needed, add together, and that is basically marginal, right? Not marginal. Magnitude, thank you. Magnitude. Interesting. dt, so that is ds. ds will be, it's a topic from arc length. Now, and this whole formula is, oh, this integral f ds is the integral from a to b. Parametrization is happening here. And now you have a function, let's call it h of t comma g of t. So you need to learn how to figure out the parametrization. And that is what we call line integral over c. Line integral of f over c, like so. So let's figure out these things. When we ask you to figure out, oh, this is a really good problem. Let's do this. Example. If I give you this x squared y ds, and I say that c is x squared plus y squared equals 4 in the first quadrant, like so, then you kind of stuck, you freak out because you don't remember which one is that. It is with a derivative, with a square root, or just the dot product. There were so many of them. Remember, it's supposed to trigger you. This ds part is a square root. So that is the formula with the square root. The formula with the square root tells you need to create parametrization first. Solution. First, sketch the picture, or don't, but at least imagine what is happening. This is the full circle with its radius 2, but it says only first quadrant. First quadrant means x and y and z are positive. So this is what is happening here. X equals r cosine t, y equals r sine t, where t is from something to something. That's the typical parametrization. So now you have to change it for your concrete example. R is your radius in 2D. So it's going to be x equals 2 cosine t, y equals 2 sine t. Check the last keys. I posted all the keys for the last quizzes. Check these. But to make sure it's not running too much, you need to check how to stay from this point, go to this point. Also, direction matters. So in this case, it says it was and control clockwise, like so.
Yes.
Wow. Counterclockwise, CCW. So it means you need to be here at 0, 0, and then it's important that you end up to be at 0, 2, not at 0, minus 2. To check that, you plug different kind of values for t and end up to have very typical example from 0 to pi over 2. Like so. Again, t is the angle, but also we usually see t as time. When time passes from 0 to pi over 2, sine and cosine keep rotating forever, but they stop at some point. And you need them to stop at that point at the top. You can always check it by plugging things in. Yes?
Isn't it 2, 0, and then 0, 2?
2, no, so we are here at the point A, 0, 0, and then we go up to 0, 2. X is 0, Y is up 2.
No, it is 2, 0, because the origin is 0, 0. Point A is 2, 0.
Oh, that's what you mean. Oh, I see. You mean this one?
Yeah.
2, 0. Thank you. Yeah, okay, good. And this is 0, 0. Yeah. This one is t equals 0. That's what I wanted to say. T equals 0, and this one is t equals pi over 2. So it's like a third dimension we added up as a parametrization. Yes.
What if it was clockwise?
There's so many combinations of this. So I will make a very classical one. Don't be afraid on the exam, but to check others, check the review and practice exam. I can go through so many combinations right now. What if it was upper part clockwise, lower part counterclockwise? That's the creative part of it. Either you put a negative sign somewhere, or you change with sine and cosine. That also helps. So that is fun, the idea to play with that. But kind of also annoying, because there's no unique answer for that. Step 2, yes?
How did you figure out it was pi over 2? Why is it not 2 pi? It's a full circle.
The full circle, the full circle will be the whole thing, but it says the first quadrant.
Oh, okay.
Yeah, it says that, yeah. And counterclockwise also said it in the question. So, let's convert the integral over c, x squared y ds. The first part is simple. Now x and y are converted into t. So it's going to be integral x squared is 2 cosine t squared. Y is 2 sine t. Here it is. So we did that. That was fantastic. Good job. But now what is ds? And ds is bs. ds, nothing. I have made a bad joke. Is the huge square root. What kind of square root? You take derivative and square each. I would not do it separately. Too much time taking this on the test, you know. Just put it at the end and you know it's going to be dt. Figure out the derivative of 2 cosine is minus 2 sine. But then you square it, so who cares the sine? It's going to be 4 sine squared t. Done. Can you do that fast? Just kind of... No negative signs because it's squaring anyways. Derivative of 2 cosine is 2... Derivative of 2 sine is 2 cosine. It's going to be 4 cosine squared t, like so, dt. So don't forget, you differentiate derivative squared. Makes sense? Done. Comes from the parametrization. Now, it's obviously square root of 4. So that's exactly what we're trying to give you, square root of 4, which is 2. And then you finish, either you finish integration or you choose it from the multiple choice part. Also, we did not finish t. t is running from what to what? From 0 to pi over 2. Done. So it's integral from 0 to pi over 2. Collected terms is going to be 2 times 2 times 2 is 8. Cosine squared is cosine squared. Sine stays sine times 2. Oh, okay. So 2 times 2 times 2 times 2. That's 16. dt. Done. Can you do that? That is the example with ds. If you need to keep integrating it, that's your substitution. U substitution. You choose cosine. Maybe make a note. That is u sub. U is cosine t. And then you keep going with u substitution. So that is a good example to put on a test. It's fast, convenient, nothing tricky is happening here.
To you.
Well, yeah, I don't say it's easy. That's true. I'm very careful about that. The phrasing, I don't call it easy. I would say it's fast at least. You have to admit it is fast. So, again, on the exam, I put ds there. Done. You know what to do. Fast, convenient. And what if I even gave you parametrization? What do you think about that? How convenient if I did? What if I did not give you example 2? What if I just gave you the integral, I don't know, x, what was it here? X squared y, x times 2y cubed ds. And what if I gave you r right away? What is r? R is this. So maybe this is something important to point out, that this is r. You are building it as 2 cosine t, 2 sine t, right? And then you're finding r prime, and then you find the magnitude of r prime. These are 3 steps you're doing here. 1, 2, 3. For this work, that's called r. What if I give you r? What if r is already 2 cosine t, 2 sine t, and then say third variable like 5t, and then I give you t is from 0 to pi over 2. What if all of this is given? Given. Can you imagine that? How would you do that one? It would be so fantastic because x is already given. This is your x, maybe sign it. This is your y, and this is your z, right? Z, so it's 3-dimensional this time. It will be 2 cosine t, 2 y is 2 sine t cubed multiplied by ds. ds is a square root of, differentiate each, squared. Derivative of 2 cosine minus 2 sine, I don't care, 4 sine squared t plus 4 cosine squared t plus 5 squared dt. T is from 0 to pi over 2. Can you do that? Boom, done. So that is even easier. If I give you r, you should just remember what r is. R is a collection of the parametrization you're supposed to be creating, but I created it for you. And then you finish integration, and I just will try to give you something avoiding integration by parts, which I was given for this exam. I'm like, are you guys kidding me? You want me to tell students to do integration by parts? So I was figuring this out. That was a weird decision. Why would you put integration by parts on the exam? That's not calculus 2 anymore. Yes.
What's the solution to the first example?
8 children.
16/3.
Yeah, 16/3. I also remember that. We have it in the notes, so you can read it. Yes.
I have -2.
Yeah, I have negative.
I got 16.
I got positive 16.
Yeah, I got 5.
We will not be checking this out. Those are numbers, okay?
So, so for that you just did for number 2, is that just the f times dr? I mean, you use that what we did. It's like you just find the derivative.
So that's a good question. So that was a good question right now. So what we're doing here, idea is integral over c f ds is integral of f, but now it's of t, stuff of t, right? Like so, times this square root is r prime magnitude. That's one of the ways to see the same formula. It's the same thing as integral of f, right? And then this square root of x prime plus y prime plus z prime each squared. Same thing. So you're right. It is f r prime magnitude.
Okay, so that FDR, like dot product thing, that's something.
That's different.
Okay.
That's different. Yeah, we're gonna do it right now. Let's move on. So this was line integral over the vector field ds. You see ds. Now, how about collecting all those little things on the way? That is the one you're asking about. That is coming from this idea. This is coming from the integral of vector field, line integral of the vector field. When we put this line integral into the vector field, line integral over the vector field, then this field, then this integral now is collecting all the arrows on the way. So you're running the marathon and you're collecting with your device, say on the chest you have a device collecting all the wind that is either against you or helping you or have no idea what is going on with you, so it doesn't matter. Let me finish. So I will have integral over c f dr. That's the one. You still perform parametrization, so still we do parametrization until we learn several good theorems, green theorem and fundamental theorem. Fundamental theorem is the best one. And then it gave us this formula, integral from a to b, capital F. Now it is depending on this r again, which you create as parametrization. And then because you switched everything to t, chain rule happened. dr used to be independent variable. dr used to be independent variable. Now r depends on t, and that is why there's a tail showed up, which is r prime, which depends on t by chain rule dt. This is literally the result of the chain rule. We'll just call it tail. This is going to be a tail of each integral, just like the square root in the previous example. This is a dot product, so the answer should be a number. Remember, this number is big and positive. Wind is helping you a lot. Negative, wind is against you a lot. Close to zero, wind barely bothers you. Zero, wind is perpendicular to you, so you don't care. That is the idea here. So you will see on the exam questions like these. Write down F. So you will see find the work done. Work done. Let me actually copy it from the exam because I know. Let's see.
Please.
Work done. Let's see. F. Where is my work problem?
It's okay if you share your screen right now.
Yeah, I'm trying to carefully. No, if I show my screen, I will have to redo the whole exam, and I just spent hours yesterday doing
Just
it.
stop recording.
Find the work done by the force field. So this is going to be on a test, and these are actually pretty pleasant examples, to be honest. I think in my case at least. Then we give you F in moving an object. In moving an object. I know. Along the curve. And then we give you a curve, and then sometimes from and to. From where to where? To. From and to. So this is going to be on a test, either free response or multiple choice, or both.
Probably free response.
Probably both.
Probably both.
What?
So, how to find these problems? I will fill in the gaps right now. For that, you need to know the formula that F is your force. That is the idea behind it. And then integral, line integral F dr is this work done of. Work done by the wind F when you are running on C. You are the particle moving. So that is the idea here. For example, let me fill in the gaps. As an example, let's do F is given any kind of random vector I give you. So any vector represents this moving wind, or maybe there's a water and you're swimming and there's water everywhere. Where does it go? It's keep moving all the time. Maybe water helps you to swim, maybe it's against you, maybe it's somewhere underneath perpendicular to you, so you don't care. So F is that water. It's already moving. You are swimming somehow. For example, as a parabola, y equals x squared. Say you're swimming on the parabola, but not the whole thing. It's infinite. Oh, this was not here. It's the curve. The parabola but not the whole parabola. Let's only do it from this point to this point. So it's like very random choices. So that's it. Your job is to create a parametrization. Let me see. Yeah, you have to create parametrization by yourself. I can see that from the exam. So we're gonna give you classical parametrization. Step 1, create the parametrization. So sketch the picture if you need it. You're working on the parabola, but not the whole thing, from this point 1, 1 to this point 2, 4. That can be represented like so. Parabola has a typical parametrization. Call x t, that's it. Everything else follows from here. Then y is x squared. But x is t, so now it's t squared. This describes the whole infinite parabola, y equals x squared. To restrict it, just tell t to run from and to. But t is x. X is running from 1 to 2, right? It's over here. X is running from 1 to 2. From 2. So it should be from 1 to 2 for t as well. And you can always check. This should be the beginning point, 1, 1, and this should be the ending point, 2, 4. When you're done with parametrization, let me finish the example to make a big picture. Then you do exactly what you did with the square root, but one step off. You don't do the square root. You will have integral c f dr. You should see it kind of triggers you. F dr, no square root needed. It's going to be integral from 1 to 2. You have your vector product, you have your dot product now, product of two vectors, dt. That is the idea of this. Force worked. The force is working to move the particle, or how the force is intervening with the particle moving, or you swimming in the ocean. So what is happening with the first vector? The first vector was x sine y, comma y. Now it's going to be t sine t squared, right? Comma t squared. So I'm just plugging my parametrization now. It's going to be t times sine t squared, comma t squared. That's what we created with parametrization. Then what is the second vector? The second vector is r prime, because it came from the chain rule. Dr now is r prime dt. That is how you should remember it. That's how I memorize it. So you differentiate your r. What is your r? Do you understand that this is the r we're building? R you build is t comma t squared. This is the r. Here it is. You building your r. So let's complete it. Derivative of t is 1. Derivative of 2t. Derivative of t squared is 2t. There's only one step missing. It's this magnitude. Magnitude was with ds case. ds was literally the area of defense, and that's why we had it there. This one has nothing to do with the area of defense anymore. This one is you swimming through the ocean, and the water is either helping you, against you, or it's somewhere at the bottom perpendicular, so you don't care. The result of this scalar product. Scalar product. I like it, this name more. This is Russian name, scalar product. Because scalar product tells you it's a number, the answer will be the number. From 1 to 2, when you multiply t by 1, you have t. T sine squared times 1 gives you t sine t squared. Plus t squared times 2t. It's 2t cubed dt. So as you can see, that gave you a function which now will be a number. When you integrate, plug the top minus the bottom, and it gives you an ugly number in this case. 1/2 cosine of 1 minus cosine of 4 plus 15. This is a very typical exam problem, so it's going to be there. Yes, now I have questions. Yes.
Yeah. I just sorry. I had a question just before. I'm just confused on where we got t and t squared. I know it's parametrization, but that's just solved by finding.
No, we did not solve it. We just explained how to describe this curve, which is part of the parabola, but only on this location.
If I'm understanding correctly, you know that from 1 to 2.
Yeah.
From t, and you just found something that satisfied that.
Yeah.
Okay.
That's exactly how I would say. Very nice.
You solved it backwards, essentially.
Yeah, yeah.
Okay.
That's how I would say it. Yeah. More questions?
See the original problem.
Oh, here it is. So whatever is in green will be on the exam. Whatever is in purple, I just randomly change it to have good numbers. That's it. Yeah.
I had a question about conservative fields.
Mm-hmm.
So, if the vector, if we can find an antiderivative for the vector, does it mean that it's conservative?
Yeah. Conservative means this antiderivative exists in the first place, but not to look forever. We first prove that it's conservative, and then we're like, okay, it's fine. Since it's conservative, let me find antiderivative. But if you already found it, automatically it means it's a yes.
And what about the py and qx? Does that also prove?
That is green theorem. Yeah, it has connection. That proves that it's conservative, and then conservative proves that the antiderivative exists.
So if py equals qx, does that mean the field is conservative?
Yeah, I think so. Let me go back to this green theorem. Green theorem will be there, and those are the best topics, to be honest. So let me do this. Just a second. There will be questions, prove that something is conservative, and find the antiderivatives. These are good questions, to be honest, because usually people do really well on these. Green theorem says, instead of doing all this stupid parametrization, you will just switch to double integral. This problem is on a test, like just different picture, but this is the problem on a test. Calculate your line integral, same dr, as you can see. Now it gives you capital F as well, and then it also gives you this. You could do it the way we just did, but it's longer this way. So it says for the free response, we're gonna tell you, no, use green theorem or else. So to be honest, you could do it the way we just did right now. Green theorem makes it easier, or sometimes you cannot do the original way if integral is impossible. So to go from integral which is impossible, we choose to suffer with double integrals instead, using this formula. So you have to practice this for Wednesday, because it's going to be a free response question, or else how else I can force you to use green theorem? Only on a free response to grade your work. And that means you need to review how to do top minus bottom, right minus left ideas. I will give you some simple form shape like triangle or square or rectangle. And so this problem we did last time, this is very last problem on the last class, this is going to be on a test right away. And also finding antiderivatives. Fundamental theorem of calculus is also on a test. And we're also going to force you to use it, which is actually a good thing, because it's easier this way than to do the whole thing again. This one says, here it is, f is conservative, then not only antiderivative exists, but the line integral is easier to calculate, because you don't have to do any parametrization anymore. We will ask you to find antiderivative, so practice that, and I will do more examples like this on Tuesday, tomorrow.